Okay, so last time we stopped at isomers, specifically structural isomers, where we learned that isomers are compounds with the same formula but different arrangement of the atoms or different connections of the atoms. On this meeting, we'll be talking about resonance and the geometry of an organic compound. So for resonance structures, they are Lewis structures with the same placement of atoms, but a different arrangement of molecules. So remember, isomers are different or similar chemical formula, but same or different attachment of atoms. For resonance, they are not isomers because their atoms are arranged similarly. It's just the electrons that are differently positioned. So for example, between the two, there is a double-headed arrow which indicates that these two are resonance forms. Okay, what's different between them? So if you take a look at the, the left structure, you have here the oxygen bonded to your carbon through a double bond, and it has two lone pairs. And the nitrogen next to it has two lone pairs and is singly bonded to your carbon. On this side, you notice that the nitrogen now is doubly bonded to the carbon, and the oxygen is singly bonded, and it now has three lone pairs. So these two are called resonance forms. Okay, resonance structures, we have to remember, are not real. Okay, emphasize on not real. Why is that? These resonance structures are simply theory or constructs that is aimed to explain the empirical data that laboratory chemists obtain. Okay, so they're actual data which the proposed single structure cannot explain. So therefore, they proposed or they come up with resonance structure to try to explain behaviors of compounds. Now, resonance structures are not in equilibrium with each other. Okay, remember that double-headed arrow that we use for equilibrium. Okay, in this case, it's just a single line with two heads, arrows, but it does not mean equilibrium. It just means equal forms. Okay, it's not equilibrium. And then again, they are not isomers. Okay, they're not isomers. And you also use resonance structures for when you have a molecule, but it cannot be adequately represented by Lewis structure. Okay, for example, these two valid structures of uh, which is HCO and H. Okay, that's used for resonance structures. Now, resonance structures are just again different ways of drawing the same compound. Now, the two resonance structures are not different. Notice here, for example, structures A and B. Your carbon here is triply bonded to your oxygen. That means a lone pair, in this case, is used as a bond. But if you look at structure B, that lone pair that is used as a bond is now a free, unattached, or non-bonded pairs of electrons. Now, these two, they are resonance forms. Their atoms are arranged or attached similarly, so they're not different compounds. They're just resonance forms. If you take a look at structures C and D, you notice that the oxygen is bonded to an H in this case, and you have a double bond here in the first two carbons, whereas on structure D, the oxygen is doubly bonded to a carbon, and then there is a hydrogen attached to the first carbon instead of to the oxygen. Because they are differently attached, the atoms are differently attached, we call them isomers. They're not resonance forms, they're different molecules, so they're isomers. So just to emphasize, resonance forms are not isomers. They're the same compound. Okay, how do you draw resonance structures? There are three rules. The first one is that the structures differ in position of multiple bonds and non-bonded electrons. The placement of the atoms, again, always stays the same. So in this case, you have C bonded to an O. Okay, for this structure in A, you have C bonded to an O next, and it's also bonded to an N, and then H, and then another H. In this, the resonance form is still bonded to an O, an N, an H, and then there's next to an H. What's different? They're double bonds. Okay, the multiple bonds are positioned differently. The non-bonded pairs, that's the one is in N, it's now in O, are positioned differently. So that's the first rule. Single bonds always stays the same. Only the multiple bonds and lone pairs are different. The second rule is that the structures must have the same number of unpaired electrons. So pay attention to the number of unpaired electrons. So you have one pair, two, three, four in structure A. In structure B, you have one, two, three, four. That's the same. Whereas if you take a look at structure C, you have one, two, three, four, and you have an unpaired single dot here. These two, which tells you that C is not a resonance form of A and B. Okay, because they should have the same number of unpaired electrons. Okay. The third rule, they must be valid Lewis structures. So there will be times when you would only be given a formula and then you come up with a Lewis structure. And then you would evaluate your Lewis structure if it's valid, and then if you could form a resonance structure of it. Okay, in this case, for carbon here, you have 1, 2, 3, 4, 5 bonds or 10 electrons around carbon, which makes it an invalid Lewis structure. Now, for drawing Lewis structures, you use the curved arrow notation. This is just a convention which tells you that which tells you how the electrons are positioned and how they are different for the two resonance forms. A curved arrow, says here, always begins at an electron pair. What does that mean? Electron pair, so it could be a bond or it could be a lone pair. In this case, for example, okay, this arrow here started from a bond, okay, from a bond, and then it formed into a lone pair, okay. Whereas in this arrow here, you have a lone pair where the arrow starts and which ends to a bond. Okay, that movement could be seen. It could be seen here, right? That is that particular movement of your electron, and the other one would be this here, that change in the form or location of your electron. Okay, so again, the tail starts from the lone pair or the pair of electrons that you will move and ends where the electron would position. So it could be on an atom or as a bond. Okay. Let's take these two for example. So follow the curved arrows to draw a second resonance structure for each ion. Right, so start with placing the single bonds, because as we said, the first rule, the single bonds has to be the same. All right, so you started with, you moved your pair, so this is from bond, okay, from bond to bond. All right, so from bond to bond, meaning that pair of electron will move towards here, and that will look like this. Okay, now where did our charge go? To determine the charge, after you have drawn or repositioned your electrons, you now have to assign formal charges. Okay, remember formal charges. For this particular see, this C, okay, it's the same as that one. Pareho lang sila. You have two single bonds and one double bond, so the formal charge shouldn't change. But for this carbon here, from single bond, naging double bond. So we have to find its formal charge, which would be the number of valence electron. In this case, that's 4, minus the number of non-bonded electrons. So you don't have a lone pair here, that's 0. Minus the number of bonds. So in this case, that's 4. That would be from the double bond and two single bonds attached to your hydrogens. So that's 0. For this particular C, there is also a change because from double bond, it now has a single bond only. So let's try finding its formal charge. That's 4 minus 0 minus, so that's 1, 2, 3. Only 3 bonds equals positive 1. So then our charge, the positive charge will end up in this carbon. And that is your resonance form following the curved arrow notation. Okay. For example B again, right? Let's start with drawing the single bonds. That's a carbon, carbon, and oxygen. A hydrogen here, and another hydrogen here. And then it says that for the first arrow tells you that the lone pair starts from the lone pair and it went to a bond. So then that would be looking like this. And the second arrow points from the bond towards the atom, which tells you that that bond will now become a lone pair on this. Sorry. Okay. It becomes a lone pair on this particular oxygen. Okay. Now let's see. The oxygen has changed its positions of electrons. So from double bond with C, it's now single bond. And then it has now 3 lone pairs. So then we have to find its formal charge. So that's valence, which is 6 for oxygen, minus 1, 2, 3, 4, 5, 6 electrons, free electrons, minus 1 bond. That gives you a negative 1, which tells you that your negative 1 charge ends here. But just to double check, okay, let's just double check. Let's see this one because it has changed positions in your lone pairs. So Fc for that carbon would be 4, minus it no longer has a lone pair, so that's 0. And then minus 4 because it now has 4 bonds, including the new bond formed from moving that pair of electron. So that's 0. Okay, so this is now our resonance form following the curved arrow notation. Okay, more examples. This time we are told to indicate the curved arrow to show the movement of your electrons. So from here, you have single, double, single. It became double, single, single. So what that appears to mean is that this particular pair of electrons over here went from here to towards this side. So just to represent that, as your curved arrow, like that. Okay? And that's it. That should be the curved arrow notation that would lead you to this structure. Okay, let's do that again. For this one, evaluate. Okay? This oxygen used to have double bond. On this side, it no longer has a double bond. So that tells you that this pair of electron here, which is a bond, went and moved towards the oxygen atom. And then this here, which does not have a double bond, became a double bond. And there's two less electrons pairs here, which again tells you that one of the pairs moved towards the bond to form the double bond. So that just tells you that the curved arrow would look like that. And uh, okay, and that's it. That is your curved arrow notation. So recap. A curved arrow notation shows the movement of an electron pair. Okay, so it begins at an electron pair, which could be either a bond or a lone pair, and then the head points to where the electron pair moves. So it moves. How does it move? It could form a double bond. Okay, it could be used to form a double bond, or it could become a lone pair. Right. Let's see more examples. Or when do you decide to draw a resonance structure? Okay, when is a resonance structure possible? Okay, now this course is just intended for introduction to resonance structures. If you'd be interested to continue on with studying organic chemistry, you would find patterns of bonding that would tell you that there is a possible resonance form for a certain structure. Now, for this course purpose, okay, I would introduce you to two situations where there is a possible resonance form. Okay, so the first one here was that when a lone pair is located on an atom directly bonded to multiple bonds. So what does that look like? So you have here, okay, you have this carbon with a lone pair that is next to a multiple bond. Okay, a carbon with a lone pair bonded to a carbon that has a multiple bond. So when there is such a situation, then you know that you could draw a resonance structure. So what happens? Your your lone pair moves towards to form a double bond, and then that double bond that's next to it will form a lone pair to the next bonded carbon. Now, in this form, the other example, so you have here a carbon, okay? You have here a carbon with a lone pair, and then a carbon bonded to, doubly bonded, multiply bonded to an oxygen. So again, lone pair connected to a carbon with a multiple bond. That's when a resonance structure is possible. So that's one situation. The other one is when there is a positive charge that is bound to either a multiple bond or an atom with a lone pair. Okay, so notice that we only said a lone pair next to a multiple bond and a positive charge next to a multiple bond. Okay? Walay labot ang negative charge. Kanina siya, positive charge siya. So what happens when there is a positive and a multiple bond, that multiple bond, because you know that's extra electrons, will try to compensate and get rid of that positive right there. Okay? So that is the movement, the possible movement, and you get a resonance form. Okay, in this case, you have a positive charge next to an atom with a lone pair. So again, that's extra electrons, and there's a positive or an electron needing atom here. So it will try to compensate for that positive charge for that carbon. Okay, and that's when you get a possible resonance structure. So again, it's lone pairs next to a multiple bond or positive charge next to a multiple bond. That's when a resonance structure for is possible. And again, this is just for introduction to the resonance forms. Right. So again, let me just recap those things quickly. So composite, the composite, when you have resonance forms, they're not real. What's actually happening is that they are combined structures. Okay, they're not real. They're just constructs or ideas to explain a behavior that cannot be explained by a single Lewis structure. And they're not standalone molecules. They are actually composites, and you call them resonance hybrids. Okay, the electron pairs drawn in different locations in individual resonance structures are delocalized. What that means is, again, it's not a standalone structure. Every resonance form is not a standalone structure. And the real structure is that it's in between the resonance forms that you have. And the idea is that your electrons are not owned specifically or exclusively by one carbon or between two carbons in a bond, but they are actually delocalized or continuously moving between your structures. Okay. The resonance hybrid is the more stable resonance form because the electrons are delocalized and is distributed over a larger volume. When you have two or more resonance structure, there is a better resonance structure that could explain the hybrid form more, and we call that the major contributor to the hybrid. All the others would be minor contributors. Now, how do you decide that a resonance form is the major contributor? Okay, the better resonance structure is the one, okay, take note of this, it's the one with more bonds and fewer charges. More bonds, as in this case in our example, structure X has double, single, single, so that's 4 bonds in all, whereas structure Y here only has 3 single bonds, and you have multiple charges of positive and negative in your structure. So that means X here is your major contributor and Y is a minor contributor. That is contributor to the proposed hybrid or composite resonance hybrid structure. So what does the composite or hybrid look like? So for a hybrid, okay, in this example, you have these two A and B as the contributing structures for this particular species or ion. And if you combine them or you come up with a hybrid structure, notice these ones, the broken lines. That tells you that the electrons or these double bonds here aren't exactly double bonds, but that your electron pairs are continuously moving between these two. So you're reverting from C double bond O to C double bond N structures. And this is your resonance hybrid. Also, because your electrons are delocalized or distributed, your fixed negative charges here would become partial negative charges, which means that the impact of the charge is now distributed, and which makes this a more stable structure. Now, okay, let's take for example this one. We try to decide which will be the major contributor, right? For this one, you have 1, 2, 3, 4, 5, and you have a positive charge around carbon. The resonance form given has 1, 2, 3, 4 single bonds and 2 and 1 double bond and also a single positive charge. Now remember, we want the more bonds and fewer charges. This one has more bonds. They have the same charges, so then we know that this is the major contributor. And this one, consequently, is your minor contributor. Now for these two, you see that's one double bond and 2 single bonds. The other resonance form has one double bond and 2 single bonds also. In terms of charges, they both have a negative charge. So essentially, they are equal structures, so they will be equal contributors. For the assignment, you're given here the Lewis structure of nitrous acid. You'll come up with the resonance structures and then label them if they're major, minor, or equal contributor. Please pass them on Friday. Okay, so that's for resonance forms. Now we go to determining molecular shape. Now there are two factors that determines the shape of a molecule, and that is bond length and bond angle. For bond length, the average distance, which is the average distance between the centers of two bonded nuclei or two atoms. Okay, if you go from left to right of the periodic table, you know that the periodic trend for atomic size is decreasing. Okay, left to right is decreasing. So carbon, nitrogen, oxygen, for example, here, that's going from left to right, then you know that the size is getting small, and consequently, if they're bonded to the same atom, H, for example, here, the bond length will be decreasing, or in reverse, if you go from right to left in terms of bond length, it's increasing. If you move from the top to the bottom of the periodic table, the trend for size is increasing. Consequently, if they're bonded to the same atom, hydrogen again for this example, from top to bottom, because the size is increasing, the bond length would also be increasing. Okay, so that's the trend for bond length. Now, for bond angle, which is the shape, which determines the shape around any atom bonded to two other atoms, we would utilize the VSEPR or the VSEPR theory. Okay, this is the valence shell electron pair repulsion theory, which tells us that if you have electron groups or groups around a single atom, the arrangement will be most stable if these groups are positioned as far away as possible from each other. Here, when we say group, okay, it's either an atom or a lone pair. For example, if you have water, the water molecule, okay, the water molecule has two hydrogens attached to an oxygen and then two lone pairs on the oxygen. So if we say how many groups, if we ask how many groups are surrounding your oxygen atom, you have to count the lone pairs. That's 1, 2, and then the atoms. That's 3, 4. So then there are 4 groups bonded to the oxygen. That is how you determine the number of groups. Now for geometry, if you have two groups bonded to your atom of interest, they will have a geometry that is linear, wherein your two groups are as far apart as possible, or that's 180 degrees angle. If there are 3, the geometry will be trigonal planar. The groups will be separated by a 120-degree angle. And if there are 4 groups, that would be tetrahedral. And the atoms or the groups will be separated by a degree of by an angle of 109.5. Okay, let's take samples. I only would like to focus on these 3. But the fact is there could be 5 groups, 6, 7, or as much as 8. But these are more common in inorganic compounds. For organic compounds, wherein we deal mostly with carbon, I'll be focusing on these 3 groups and these 3 types of geometry. Let's take a look at groups with linear geometry. That is a group with 2 atoms bonded to your, or 2 groups bonded to your central atom. For example, beryllium dihydride. So you have Be surrounded by 2 atoms of hydrogen. So you have a linear molecule. In this case, you have carbon bonded to hydrogen and another carbon, so two groups. Then we call that also linear. Okay. And then this another carbon here bonded to hydrogen and another carbon, so two groups separated by 180. That the geometry around that particular carbon is also linear. If you take a look here, that is the ball and stick model of this particular compound, which we call ethine. The naming we will learn later. And it's linear. For three groups, okay, you have boron trifluoride, for example. So you have a boron surrounded by 1, 2, 3 atoms. So trigonal planar is your geometry. For your organic example, we have a carbon here, okay, one carbon surrounded by 1, 2, 3, okay, three groups, so trigonal planar, and then this other, okay, this other carbon surrounded by 1, 2, 3, and that's three groups, which also tells you that's trigonal planar. And if you take a look at this one, they all lie in one plane, meaning if there's a paper behind that particular structure, all the atoms will touch the surface of that paper. So they all lie in one plane. So this is ethene or ethylene. For carbons with four groups or atoms with four groups surrounding them, I'd like to focus on methane, which is a carbon surrounded by four hydrogen. Since there are four groups surrounding your carbon, then we call it, the preferred geometry is tetrahedral. Okay, so that's a tetrahedral. Notice that they are separated by angles of 109 degrees. It doesn't look like this. Okay, this one looks planar, where your hydrogens are separated by 90 degrees. They're still pretty much close to each other in this case, so the optimum or the preferred geometry is tetrahedral. So they don't exist like that. So in a 3D form, okay, if you think of your carbon nakadikit sa paper, na ay duha ka hydrogen nga nakadikit pod sa iya ha. Okay, think of it as a paper. Nasa sa paper, nagdikit. Ang kaning duha ka, the other two, the one would be protruding sa likod. Okay? Naglapos sa likod. And the other would be naglahos diri sa atubangan. Okay? It's pointing towards you sa front. And then that one sa back, towards the back. Because this is solid wedge to indicate facing front, and the broken wedge is facing or protruding at the back. So that's how you write a 3D representation of a tetrahedron, okay, or a tetrahedral structure. Right, so notice that we've learned about the chemistry of carbon is that it's tetravalent, meaning it's capable of forming four bonds. It preferably forms four bonds. But you notice in our examples that those four bonds, okay, could either be forming a linear geometry, okay, in case of carbon to carbon triply bonded, or it could have a trigonal planar geometry, or it could have a tetrahedral, okay, a tetrahedral geometry. Okay? All right. Now let's try and evaluate these two for the geometry around the indicated carbon. That's for your assignment. This is also an assignment. Okay. Uh, you put this as additional assignment for Friday. Thank you, and I hope you find this video instructional helpful.